What if your problem does not conform to a standard use case? Let's say we want to compute the maximum difference between old and new temperatures. For instance, the first object cooled from 42 to 31 degrees, which is an 11-degree change, but the last one cooled from 50 to 35, a difference of 15 degrees. So the maximum difference is 15 degrees. There's no standard algorithm for computing this, though. A naive approach would be to compute each stage of the algorithm as illustrated. To do this, we start by creating a vector for differences. Then we use the version of thrust transform to take two input ranges, one for the old temperatures and one for the new temperatures. Our operation, a lambda or function object, now receives two parameters, one from each range, computes the absolute difference between them, and writes the result into the differences vector. Lastly, we run a max reduction on the differences vector to find the maximum absolute difference. This code will produce the correct result, but is it efficient? To answer this question, let's recap the key steps of this algorithm. It starts with an allocation, which is already suboptimal. After that, it transforms two input ranges into differences. To build an intuition for this step, you can consider the transformation as a for loop shown here. Inside this loop, we read two elements, one from A and one from B. We then compute the difference and write it back into memory. Overall, this step reads 2n elements and writes n elements back. The subsequent reduction step can be represented as another for loop. Here it reads one element from the difference array, checks if the newly read value is larger than the current max value, and updates the current max value if it's the case. Overall, this approach leads to 3n reads, where n is the size of the input sequence. It also writes back n elements. The question is, if you had to implement this algorithm with just for loops, would you write it this way? To make this more efficient, we can rewrite the logic using a single reduction loop. Instead of computing all the absolute differences ahead of time, we can calculate them on the fly as we iterate through the elements of A and B and immediately compare each result to the current maximum. This approach only reads 2n elements, each element of A and B once, and avoids any extra memory allocations. Since it cuts memory accesses in half, we'd expect a noticeable performance gain. So the natural question is, how can we implement this on-the-fly computation using a parallel algorithm? And which parallel algorithm should we use? Thankfully, this part is straightforward. Our loop already behaves like a standard reduction, except we're reducing absolute differences rather than raw values. That means the right tool is thrust reduce. But how do we plug the absolute difference logic into thrust reduce? The answer lies in iterators. And if you're not familiar with them yet, don't worry, we'll cover the essentials next. The simplest way to understand iterators is to start with something familiar, pointers. In this example, we allocate the array with 3 elements, then create a pointer that points to the first element. Using the subscript operator, brackets, we can access elements of the array through the pointer, just like we would with a regular array. This works because pointers act as basic iterators over a sequence of values in memory. Here's a simple mental model for understanding pointers. A pointer stores a memory address, the location of some data in physical memory. In addition to storing that address, pointers provide an array-like interface for accessing the data. For example, accessing index 0 through a pointer gives you the first element. Index 1 gives you the second, and so on. Each step moves through memory based on the data type's size. But the subscript operator isn't limited to pointers and arrays. If you think about how we access elements in thrust vector or std vector, we use the same square bracket notation. Why does that work? Because in C++ we can define the subscript operator, the brackets, just like any other function. In other words, when you write vector at index 42, 42 is passed as a parameter to the subscript operator function inside the vector class. This flexibility allows us to give many objects pointer-like behavior, which brings us to iterators. Since we can put any code in the subscript operator, we don't have to limit ourselves to the concept of physical memory at all. For example, imagine a type whose subscript operator just returns whatever index you pass in. Pass it 42, you get 42. That might seem pointless at first, but by the end of this course, this little trick will become one of your best friends. So now let's compare the pointer-based code on the left with our custom type on the right. When we pass in an index of 0, both print 0. When we pass in an index of 1, both print 1, and so on. Functionally, there's no difference. But because a pointer is tied to actual physical memory, every time you use the subscript operator, you're performing a memory access. That means if you read n elements, you'll have n memory accesses. Our custom type, on the other hand, simply returns the index you passed in with no memory access at all. In theory, that can give much better performance. And from the algorithm's point of view, notice how both interfaces look exactly the same. We just use square brackets. Whether those brackets trigger a memory read or simply return the index doesn't matter for the rest of the code, and that's a key concept behind how iterators work. You can think of iterators as a generalization of pointers. They provide the same interface, think subscript operator, increment, etc., but they are not limited to actual memory accesses. The type we just explored is called a counting iterator. It presents an infinite sequence of integers without allocating a single byte. Here's its code just to help build a mental model, but you won't ever need to write one yourself. It's the concept that's important. The counting iterator we just saw doesn't make any memory accesses, but not every iterator works that way. For example, imagine a transform iterator that references an underlying pointer. Every time you call its subscript operator, instead of returning the original element directly, it might multiply that element by 2 before giving it back. From the outside, it looks like the entire sequence was scaled. If you look at index 1, you get 2. Even though the underlying data still stores 1. Notice that the result of the multiplication isn't stored anywhere. It's computed on the fly each time you access an element. We can take this even further by implementing a zip iterator that references 2 sequences at once. Its subscript operator returns a tuple containing 1 element from each sequence. So if we access the iterator at index 0, we might get 0, 5, which corresponds exactly to A0 and B0. The real power of these so-called fancy iterators shows up when we start combining them. For example, imagine a transform iterator that uses a zip iterator inside. Each time you call its subscript operator with index I, it first fetches 2 values, one from sequence A and one from sequence B, then computes their absolute difference and returns it. That's exactly what we needed for our maximum difference algorithm. If we pass the transformed zip iterator to a reduction algorithm, it'll treat it just like a regular pointer and read values as usual. But under the hood, every access fetches 2 elements, computes the absolute difference, and hands it over. All of that without writing those intermediate differences back to memory. In reality, production-grade iterator implementations are much more complex than these simplified examples. Luckily, you don't have to build them yourself. Thrust already provides a variety of ready-to-use iterators, including counting, zip, and transform iterators. Let's take a look at how to work with those in practice. Thrust make counting iterator takes an integer that tells it where to start counting. For example, in this code, we pass it into thrust for each to print out the first 42 elements. If we create a counting iterator that starts at 1, the output will be 1, 2, 3, and so on up to 42. Thrust Make Transform Iterator takes two inputs, an iterator to your underlying data and a transformation function to apply to each element. For example, suppose we have a thrust vector containing a sequence like 1, 2, 3. We pass the beginning of the vector as the first argument and a function that doubles each value as the second. When we iterate over the resulting transform iterator, each element is automatically multiplied by 2 on the fly. So if the original data was 1, 2, 3, 4, the transform iterator yields 2, 4, 6, 8. Importantly, these transformed values are not stored in memory. They're computed dynamically whenever the iterator is accessed. Now let's take a look at an example using Thrust Make Zip Iterator. We have two thrust vectors, A and B. The first one holds 0, 1, 2, and the second holds 5, 4, 2. We then call Thrust Make Zip Iterator A begin, B begin, to create an iterator that pairs up elements from both vectors. The element at index 0 of A is zipped with the element at index 0 of B, and so on. That gives us sequence of pairs like 0, 5, 1, 4, 2, 2. As we discussed, our plan for the maximum difference problem is to combine a zip iterator with a transform iterator. In this code, we do exactly that. First, we use make zip iterator on A begin and B begin. That gives us an iterator which at each index returns a tuple of two floats, one from A and one from B. Next, we pass that zip iterator into make transform iterator, along with a lambda function. Because the zip iterator returns a tuple of floats, that's exactly what the lambda function should have as a parameter. For each tuple, we extract the two values using thrust get, compute the absolute difference, and return that result. So for the first elements in A and B, if the tuple is 0, 5, the transform iterator returns absolute of 0 minus 5, which is 5. From the reductions perspective, it's just reading a single float each time. But behind the scenes, our transform iterator grabs two floats, one from A and one from B, calculates the difference on the fly, and returns the result without any extra reads or writes. So in total, we only need 2n memory accesses, which is exactly the improvement we aimed for. Now let's see if this reduced memory traffic actually improves performance. In this graph, we have normalized elapsed time for different vector sizes. You can see that using fancy iterators is about twice as fast as storing the temporary differences in memory. And this comparison doesn't even include the cost of allocating space for those temporary arrays. If we factor in the allocation overhead, the speedup could climb to 70 times. But performance isn't the only benefit. Fancy iterators also drastically reduce memory usage. For instance, if your GPU has 8 gigabytes of memory and each vector takes up 4 gigabytes, then you've essentially used up all available space by just storing A and B. In that scenario, a materializing approach, which needs extra storage for the difference vector, that would fail. Meanwhile, the fancy iterator-based version requires no extra space and would work just fine. Most of the parallel algorithms we've seen so far are very challenging to implement efficiently. That's why it's crucial to understand how to adapt the accelerated libraries to your unique use cases without having to re-implement them. In this exercise, we want to calculate the variance of a temperature data set, which requires us to compute the squared difference of each element from the mean. A naive approach would create a whole new buffer in memory to store these squared differences which wastes both time and space. Instead, since you now know how to handle this using fancy iterators, you'll compute squared differences on the fly, feeding them straight into the reduction without ever creating a separate array. In the code snippet, you'll see a placeholder for squared differences. Your task is to replace the placeholder with a transform iterator that computes the squared differences between each element and the mean.